welcome back. Today we're going to be doing continuity and side limits. So in order to understand the concept of side limits, we have to understand what it means to approach something from the side. So this is x naught minus, so it's just approaching x naught from the left, and this x naught plus, which is approaching x naught from the right. If we look at our number line, x naught is an accumulation point. You'll notice if we had just x naught standard as an accumulation point, we would have our delta neighborhood right here, right? Punctured because we don't consider x naught, but that's not the point. However, if we only want to consider the left delta neighborhood, then we only go over here. So x naught is the same thing as saying x belongs to the interval x naught minus delta to x naught. And x naught plus is just this other half, which is to the right. And you'll notice if you take the union, right, of these two, you'll just get your regular delta neighborhood for x naught. So recall the definition of a limit, and that is that a limit as x approaches x naught of f of x is equal to L. X naught is real and L is real. If and only if, for all epsilon greater than 0, there exists a delta greater than 0, such that 0 being less than the absolute value of x minus x naught is less than delta, implies that the absolute value of f of x minus L is less than epsilon. So let's take a look here at our graph. This is, you may remember it from our normal, but if we take a look at x naught minus delta and just x naught, right here we have our left neighborhood. If we want to take the limit just for our left delta neighborhood, we'll take this, only values of x here, and both values of L plus epsilon and L minus epsilon, so that whole epsilon neighborhood, but only for values there. So our new definition for side neighborhoods, for side limits, would be for all epsilon greater than 0, there exists a positive delta such that if x belongs to this interval, and of course you can use inequalities to tidy it up, then of course we have that f of x has to belong to our our other neighborhood. So here we have the exact same idea. For all epsilon greater than 0, there exists delta greater than 0. And again, you can use inequalities, but the point is actually understanding the concept of what this even means. So this is how side limits work. And what side limits are is that we're saying, instead of taking a standard limit, okay, as x approaches x naught from both directions, what value does f of x approach? We're asking, oh, only from the left of x naught, as x approaches x naught from the left, what values does f of x approach? Now, notice if the side limits match, then the standard limit must also match. In fact, there's a theorem. It's known as the existence of limits theorem. It states that if the limit of f of x as x approaches x naught is equal to L, which is a real number, then it doesn't have to be a real number. Then the limit as x approaches x naught minus of f of x is equal to L is equal to the limit as x approaches x naught plus of f of x. So it's saying if the standard limit exists and it's equal to a number, then the side limits both also exist and are equal to the same number. They match. And generally, the converse is true. If we can prove that the side limits match, then we could say that the standard limit is equal to that. And also, considering the contrapositive is always true, we know that if the side limits don't match, or if one of them doesn't exist, the standard limit does not exist either. So here's an example to kind of reinforce the concept. For f of x is this big piecewise function. Here, I even graphed it for you. Find the limit as x approaches 0 of f of x. Now, if we look graphically, if we approach 0 from the left and from the right here, even though there's a discontinuity, it looks like it's just going to go to this value. But let's prove it. So maybe take your time if you want to try this problem. And if not, then I'm just going to move on to the next page. So First, the limit as x approaches 0 of f of x can be divided into the two side limits. Now, we're not writing equals, we're just writing, let's consider the two side limits first. And I rewrote our f of x if you need to see it again. Now, the limit as x approaches 0 from the left, or you might say 0 minus of f of x is, the local agreement theorem, by the way, applies for side limits as well. It's just equal to here, 0 from the left. Okay, well, 0 from the left is saying if x is less than 0, right? So it's going to be this piece. And that, of course, is just going to be minus 3. And 0 from the right is going to be this piece. Notice we don't use the middle piece because we don't consider the exact value since we're doing limits. And that's equal to this. And of course, you can use, all of this and figure it out using the composition rule and limits of radicals, but you're going to get minus 3. But since these two match, of course, like we hypothesized, the limit of f of x as x approaches 0 is minus 3 definitively. So whenever we have a boundary point, which is where the function changes behavior, we have to use side limits. When we don't have a boundary point, that is to say when we have an interior point, which is not one of these values, not in this case 0, the function is going to behave uniformly on both to the left and to the right. So we can just consider the standard limit. Now you may be saying, oh, well, eventually if you go far enough, it'll change behavior, but we get to choose what neighborhood we're working with, so we can make it arbitrarily small enough so that the behavior is uniform left and right, and we only have a standard limit to worry about. So now we're going to introduce discontinuity, and I like to show it graphically first. Let's say this is our function. The idea of continuity is that can we draw the function without having to lift our pen from our paper? So we draw it along, can we do it? Maybe not perfectly, but can we do it? And it oscillates here, and then it goes up, and boom. If I want to go here, I would have to make a skip, and that's not possible to do without lifting the pen from the paper. And thus, what we're doing here, we have to do something else. This is discontinuous. So how are we going to say that? Well, it's discontinuous, but we'll prove that later. It's not continuous. This is the idea, because we have a gap. Here we have a hole, so it's not continuous because we would need to lift our pen off the paper in theory. And here we can't do it because we have a vertical asymptote. We have to keep going up, 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 and really we can't get to the other side, or else we would have to, cover this, and that's not possible. Look at this infinite gap. Even if they went in the same direction, we can never touch it. So we seem to have a discontinuity, so the function is not continuous here at the asymptote, here where there's a hole, and here where there's a gap. Here, though, although it oscillates rapidly, it is continuous because we don't have to lift our pen from the paper. So first, we're going to start by defining what continuity point actually is. For the purposes of calculus 1, we'll just say that f is continuous at x naught if and only if f of x naught is defined, meaning x naught belongs to the domain of f. The limit as x approaches x naught of f of x exists, and it's real, so it can exist, positive infinity, but it has to be real, is what I'm saying. And the last part is really encapsulates all of it. You only have to prove this. These other two just follow from the last part. But it's saying that the limit of the function at the accumulation point, x naught, is just the function evaluated at that point. In other words, if we take values infinitely close to here and infinitely close here, notice that the limit does not exist because we have this big hole, so it's not continuous, right? And that's how we're defining continuity, right? Even though the function is defined here, the limits aren't really matching, per se, the side limits. So we're going to ask the question, is sine of x continuous at x equals 3? The answer is we're going to test it. First, whenever you want to test a function for continuity, at a point, take the limit as x approaches that point of the function, and this is equal to sine of 3 because we proved that the limit of sine is just evaluating it. So yes, it is continuous because this is sine of 3. So we plug it into the plugging it in is the same as taking the limit. So yes, it is continuous by our definition of continuity at a point. In fact, we can say that we can say that the sine function and cosine are continuous everywhere, and we'll define what that means in just a second, because we proved that the limit is just plugging it in for all values. So we say f is continuous in its domain if and only if for all x not in the domain, this is continuous. So we're restating the continuity, but we're just saying, oh, but for all x naught in the domain, it's continuous at x naught. But we say it's continuous everywhere, universally, over all the real numbers, if for all real x naught, you choose any x naught, it's continuous at x naught. And note, in order for it to be continuous everywhere, going back to our definition of continuity at a point, the domain of f actually has to be all real numbers. So if we can prove that the domain is not all real numbers, we know it's not continuous everywhere. So here's an example. Is f of x, which is this polynomial, continuous in its domain? Indeed, if x naught belongs to the domain of f, and the domain of f is all real numbers, since it's a polynomial, then the limit as x approaches x naught of f of x is equal to the limit x naught approaches x naught. We're just rewriting f of x, which is equal to evaluating it at x naught, which is just equal to f of x naught. So yes, it is continuous within its domain, since we proved that without assumption of x naught, as long as it's in its domain, the limit is going to be equal to plugging it in. And in fact, since its domain is all real numbers, we can also say that it's continuous everywhere. In fact, any function that you find that we've done, like rational functions, all the trigonometric functions, polynomial functions, radicals, are continuous in their domain because we proved theorems regarding limits that we can just plug it in. So is cosecant of x continuous everywhere? Well, the domain of cosecant of x is not equal to all real numbers. So of course, no, it cannot be continuous everywhere. We already talked about that. But if x naught is in the domain, then the limit as x approaches x naught of cosecant, which is 1 over sine, by the quotient rule is 1 over sine of x, which is equal to cosine of x naught. So f is continuous domain, but the domain is not all real numbers, so it doesn't work. For our next example, I'm going to take it straight out of the 2003 AP Calculus APFRQs. Question 6. So if we let f to be defined as the following function, we're only going to look at part A. Is f continuous at x equals 3? Explain why or why not. Now we're going to go overkill here, showing all our work and all the theorems associated. For the purposes of the AP exam, though, feel free to use shorthands like plugging it in a lot of the time, not referencing theorems, but we want to actually learn, so we're going to use our theorems. Indeed, the limit as x approaches 3 of f of x. Now, we can't evaluate it here because 3 is a boundary point. At 3, the function changes behavior, right? It switches pieces. So we're going to evaluate the side limits. So this side, which is from the left by local agreement theorem, is this piece, right? It's going to be x is less than 3, and that's this piece. So we're going to plug that in, and this is just since the real limit exists, the standard limit exists, the side limit must also exist, and it has to be equal to the standard limit. So we'll evaluate it as that. And you can write out all your theorems, radicals, composition rules, but really you just need to know that it's the square root of 4, which is 2. Finally, over here, we take our right side, our right neighborhood, and the piece that we're dealing with is 5 minus x. So is it continuous there? Well, by local agreement theorem, this is just the limit as x approaches 3 plus a 5 minus x, and that's just 2. But look, the side limits match, so by the theorem we proved the existence of limits. The limit as x approaches 3 of f of x is equal to 2, and 2 is just evaluating it at f equals 3, because if we plug in 3, we're going to look at this piece, it's just the square root of 3 plus 1, so it's equal to square root of 4, which is 2. So yes, this is f of 3, thus f is continuous at x equals 3. This is going to be one of the easier problems you're going to get on the AP exam. Now, we're going to do some more intervals. We've dealt with in its domain over the real numbers. Now, what about over a specific interval? We say f is continuous over the over the interval a comma b, right? Not inclusive, exclusive, if and only if for all x naught in this interval, f is continuous, right? We define continuity in the interval by saying, oh, for all points in this interval, it's continuous at that point. Now it's continuous over this, so to speak, inclusive interval, so with brackets, if f is continuous over a comma b, exclusive, and f is side continuous at a from the right, and f is side continuous from b from the left. So side continuity is just saying that the limit as x approaches a from the right of f of x is equal to f of a, and the limit as x approaches b from the left of f of x is equal to f of b. Since if we look at a number line, if this is our a and this is our b, we only want to consider values of a going from the right and b going from the left, right? It's possible that the function isn't even defined over here, yet it can still be continuous. So that's how we want to define it, and that's totally valid. This is side continuity. And finally, although not common practice, we're just going to use it as shorthand. C of f is the interval of continuity. So you may get asked questions about intervals of continuity, although it might not be written as this. It's just shorthand. So here's a practice. Determine the interval of continuity of f if f of x is the square root of 4 minus x squared. Now, we'll factor this out, and our first step whenever doing this is to try to find out the domain. Now, you can use any method you want, maybe learn from pre-calculus or from algebra, but we'll just say, since this is square root, it has to be greater than or equal to 0, meaning that the square root doesn't have to be greater than or equal to 0. The inside has to be greater than or equal to 0. And this is true if either they're both positive, they're both negative, or one is 0 or the other one is 0. So that's a lot. So we'll solve this inequality and this inequality. So that's x is less than 2 and x is greater than minus 2, or x is greater than 2 and x is less than minus 2. We'll cross this out because this is a contradiction. It's not possible for a number to be greater than 2 and less than minus 2 at the same time. And, or x is equal to 2 or x is equal to minus 2. Now the or in intervals, in like, in this case, it's just going to become union. So we'll just have x has to be in the interval from minus 2 to 2, exclusive union to union minus 2, or x belongs to this interval minus 2 to 2 with brackets. So the domain of f is that, but that doesn't actually answer our question for the interval of continuity, but this is the step that we need to take first. Second, we have to check values. Whenever we have this interval where we have inclusivity, that's when we have to start doing other things. So we have to first look at, okay, is it continuous, right? In our definition, is it continuous in the open interval, right? And then the question is it continuous from the right and from the left on the other 2 points? So we'll go first. We'll let x naught be in this open interval. I believe it's open interval. Maybe. Yes, I think. So maybe it's closed interval. So indeed, this limit of f of x is just the limit of this, and you can write out your justification, the composition rule, but you'll figure out that, okay, it's f of x naught. Perfect. But at exactly x minus 2, the limit from the right of f of x is this. Now, notice we have to be careful here because minus 2, we just plug it in, we get 0. But we have to be careful about the right or to the left, because if we go to the left, actually, this is going to not exist. The function is not defined to the left, but to the right of minus 2, it is defined. So the easy way to do this is, minus 2 plus squared is just going to become 4 minus, because minus 2 plus is going to be a value, minus 1.9, let's say, and since the sign doesn't matter, now we're going to get a value less than 4. So we're going to get 0 plus, and of course, the square root of like 0 plus 0. This isn't technical, but it's allowing us to understand, yes, we can in fact do the side limit because it's the function is defined to the right of -2. That's f of -2, so it's continuous at x equals -2. But at x equals 2, the limit as x approaches 2 from the left of f of x is this. And of course, we plug that in. But the point is that the function is defined to the left of 2, which is 0, which is again f of 2. So back to our interval of continuity, we're going to get that the interval of continuity is -2 to 2 with brackets. So f is continuous over its domain. We already found our domain. We don't take values outside of the domain because, frankly, it's a waste of time, right? We know it's discontinuous if it's not in its domain. So that's the general strategy. Break down first, break down boundary points, and only consider interior points first, and then we'll do other stuff. Finally, we're going to do types of discontinuities. So we have a removable discontinuity, a jump discontinuity, and an infinite discontinuity. A removable discontinuity is right here. We can just remove it by filling in the point. A jump discontinuity is where we have this gap, right? It's not just a hole. And an infinite discontinuity is, self-explanatory. You have infinities. So the formal definition, if f is discontinuous at it's not a, it's x naught, then f has a removable continuity at x naught if the limit exists, right? But the function is not defined there. F has a jump discontinuity, or it is defined, but it's not the limit. F has a jump discontinuity at x naught if both the side limits exist, but they don't match. And finally, f has an infinite discontinuity at x naught if the either side limit is plus or minus infinity. It's some type of infinity. Hopefully this helped you guys, and good luck with studying side limits and continuity.